Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 5, section 6, which talks about indeterminate forms. And L'Hopital's rule. Right? So here we go. First, let's remember what indeterminate forms are. Alright, so indeterminate. The indeterminate forms are things like if I have 0 over 0, or infinity over infinity, or infinity minus infinity, or infinity to the 0, or 0 to the infinity, things like that. 0 times infinity, all right? Anything that we get like this, it's in a determinate form. Why? Because we cannot determine what it is, right? 0 over 0, I don't know. Infinity over infinity, it depends. If the infinity on top is bigger than the infinity on bottom, maybe it's infinity. If the infinity on top is smaller than the infinity on bottom, maybe it's 0. Similarly here, when we're subtracting infinities, all right? So in here, we're going to discuss how to tackle these, all right? So first, let's talk about this theorem, L'Hopital's theorem. It's really called L'Hopital's rule. And by the way, a lot of times you'll see this spelled like La Hospital. Right? But it's the same thing. L'Hopital's rule. Now, um, now here's what it says. Let f and g be functions that are differentiable on some interval, some open interval AB, right? Containing C, so that interval contains C, except for possibly at C itself. What we mean there is that it's differentiable in the entire interval. C is in that interval, but the functions may not necessarily be differentiable at C, but throughout the entire interval it is. Now, assume that g prime of x does not equal 0 for all x in that interval, right? And again, except possibly at C itself. I'll leave that as just that at that. If the limit of f of x over g of x as x approaches C produces an indeterminate form, or indeterminate of these 0 over 0, infinity over infinity, and these could be plus or minus, right, on both of them. 0 times infinity, and all the other ones, right? So if I put this some indeterminate form, then we can do the following. So we have the limit as x approaches C of f of x over g of x. what we can do is take this limit, the limit as approaches c of f prime of x over g prime of x, provided that limit exists. Alright, so I'll put that there. Provided the limit on the right exists. So, I guess I could say here, or is infinite. Because technically there, it doesn't exist, but it's no longer indeterminate. So what are we really saying here? What we're really saying here is, if we're comparing two functions, right, through division, and we're trying to figure out what their limit is, and we ended up with an indeterminate form, well, what we can do is we can take the derivatives. All right, essentially we can look at the rates at which the functions are growing to figure out which one may be growing faster. All right, essentially if the limit on top, the rate of change on top is larger than the rate of change on bottom, if it's significantly larger, then the whole thing will end up going to infinity. But if the rate on the bottom is significantly larger, significantly larger than the limit on top, then overall the function would be going, the limit would be going to 0. So let's see some examples. Here. And we'll start out easy. So we're going to find some limits here. So the limit as x goes to 0 of e to the 7x minus 1 over x. Alright, let's see what happens here. When we take the limit as x goes to 0, well, what we normally say here is plug in the 0, so I have e to the 7 times 0 minus 1 over 0. Well, that produces 0 over 0, right? E to the 0 is 1. 1 minus 1 is 0. And we don't like that. We have 0 over 0. That's indeterminate. So what can we do? But what we can do now is, instead of doing that, we can apply L'Hopital's rule. All right? And that's how I like to show that I'm about to use L'Hopital's rule. All right? Put that L'Hop over the equal sign. So I need to take the derivative of the top, 7e to the 7x, over the derivative of the bottom. And now, we'll take the limit as x goes to 0. 7 times 0 is 0, e to the 0 is 1. So I end up with 7. Alright, so it turns out in this case that 0 divided by 0 was 7, essentially. Right? I don't want to say strictly divided by, but that limit itself went to 7. Alright, let's do a different example. B. Let's say we have the limit as x approaches infinity of ln of x over x. Again, this is in a determinate form. How come? Because, well, if I plug in infinity, ln of infinity, that goes to infinity. Infinity on bottom, infinity. And we don't like that. It's in a determinate form. So again, what we can do here is take L'Hopital's rule. And what we end up with here is the derivative of the top. So let me just write down my limit. The derivative of the top, 1 over x, over the derivative of the bottom. And now, there's nothing wrong with taking this limit, right? I have 1 over x over 1. And as x goes to infinity, 1 over x goes to 0. So we have 0 over 1, which is just 0. Next one. So that was B. C. Let's say that I have the limit as x approaches 0 of sine of 5x over sine of 3x. Now this limit you should recall from Calc 1, how to figure this out. There are algebraic ways to figure this one out. Because, I mean, if I plug it in, right? 5 times 0 is 0, sine of 0 is 0. Similar idea than here, 0. So we get 0 over 0 indeterminate form. We don't like that. And like I said, in Calc 1, we have ways to go around it here. But now that we've got this new rule, L'Hopital's rule, we can say, well, now we get the limit as x goes to 0 of the derivative of the top, 5 cosine of 5x, over the derivative of the bottom. And at that point, as x goes to 0, cosine of 0 is 1. 1 times 5 is 5. Similar reasoning, we end up with 5/3. All right. Next one, D. Let's say we have the limit as x goes to infinity of x cubed over e to the x over 2. If I just plug in infinity, infinity cubed, infinity. Plug in infinity down here. Infinity divided by 2. Well, that's still infinity. And e to the infinity is infinity, which we don't like. So what we can do here is take the derivative, right? Apply L'Hopital's rule. So we end up with the limit as x goes to infinity of the derivative of the top, 3x squared, the derivative of the bottom, 1/2 e to the x over 2. And now let's take that limit as x goes to infinity, infinity, right? X infinity squared is infinity. And on the bottom, I still end up with infinity. Now, that's still indeterminate. So it turns out we can apply L'Hopital's rule again. All right? And we can continue to do so as many times as we need. The derivative of the top, 6x. The derivative of the bottom, 1/4 e to the x over 2. Take the limit as x goes to infinity. Again, infinity over infinity. So apply L'Hopital's rule again. Right? And when we do that, well, now we see, well, what do we get? The derivative of the top, 6. The derivative of the bottom, 1/8 e to the x over 2. And now as I let infinity go to, as I let x go to infinity, well, notice that on top, I still have 6. On the bottom, e to the infinity, infinity divided by 8 or times 1/8 is still infinity. 6 over infinity, that goes to 0 because it's a constant number divided by a huge number, a huge quantity. And look at that. So in here, we just saw that, well, L'Hopital's rule can get applied as many times as needed. All right. Let's do another one. H. Let's say I have the limit as x goes to 2 from the right of 8 over x squared minus 4 minus x over x minus 2. All right, let's see what we get here. If I plug in 2 squared minus 4, that's 0. So I end up with 8 over 0 minus, plug in 2 over here, I end up with 2 over 0. Well, in here, well, let's see. We're approaching 0 from the right, so we end up with a positive 0 here in both of these cases. What do I mean by that? Think about a value that's to the right of 2, like 2.1. 2.1 squared minus 4, that's going to be a positive value. 2.1 minus 2, that's a positive value. So that's what I mean by we have positive zeros. So when we have something like that, what we essentially have, it goes to infinity. So we have infinity minus infinity. But what is that? Well, let's figure it out. That's an indeterminate form. So we need to manipulate this somehow. Well, in here, I see that the denominator over here can be factored. And when I factor, I have x plus 2 times x minus 2. I'm going to come up with a common denominator. Limit as x goes to the infinity of x plus 2 times x minus 2. And this is 8 minus x times x plus 2. Alright? And if I distribute it out, we'll end up with the limit as x goes to 2 from the right of 8 minus x squared minus 2x over, and I'll leave the bottom as it was, x plus 2 times x minus 2. Alright? And now let's see. I mean, if I plug in 2 squared, 4. 2 times 2, 4. 8 minus 4 minus 4, 0. If I plug in 2 on the bottom, 4, 0. 4 times 0 is 0, so I have 0 over 0. So now that I've got this fraction of 0 over 0, right, now I can actually apply L'Hopital's rule. So if I apply L'Hopital's rule, right, what I get here is the limit as x approaches 2 from the right of negative 2x minus 2 over, let's look at the bottom as not x plus 2 times x minus 2. I'm going to look at it as x squared minus 4. The derivative of the bottom is 2x. Alright? And now, let's see. Now that I plug in 2, negative 2 times 2, negative 4. Negative 4 minus 2, negative 6. Plug in 2 on the bottom. 2 times 2 is 4, which gives me an answer of negative 3/2. Notice that I stopped taking L'Hopital's rule, right? Unlike in the last example, where I took L'Hopital's rule over and over again. And I just realized I somehow went from D to H. That should have been E. But my point, the point here is that I didn't apply L'Hopital's rule again here. How come? Because this was no longer in indeterminate form. L'Hopital's rule only applies when it's in indeterminate form. But if I were to apply L'Hopital's rule here, I end up with negative 1. But that's wrong. Right? I end up with negative 1 because I end up with negative 2 over 2. Right? And that's wrong because that's not what's going on here. We can't just apply L'Hopital's rule to any limit. It must be in indeterminate form. So let's look at another example of this, or something like this. So that was E. So F let's say we have the limit as x approaches infinity of e to the x minus x. Now in here, when I plug in infinity, well, what do I get? E to the infinity is infinity minus, plug in infinity. Look at that, infinity minus infinity. Now that's indeterminate. We don't like that. So what can we do? Well, now this one's tricky because we don't actually have a fraction here, right? And even if I put it all over 1, I can't take the derivative of that because that's not what's making this be indeterminate. Not just that, I would end up with 0 on the bottom. So in here, what we're going to do is, well, there's always 2 things we can do to any math problem. And those 2 things are add 0 and multiply by 1. In this case, I'm going to multiply by 1. And that 1 is the conjugate of that statement. Notice that fraction right there is just 1. So in this case, well, what do we end up with? Well, we end up with the limit as x approaches infinity of, look at the top. In the top, I've got the product of conjugates. The product of conjugates is the difference of squares. On the bottom, we still have e to the x plus x. And now I've got a fraction that I can work with, right? Now we can apply L'Hopital's rule. And if I apply L'Hopital's rule, well, what do we get? I have to take the derivative, right? And by the way, this is still an indeterminate form, right? Because we have infinity minus infinity over infinity plus infinity. The bottom is not so much a problem because, well, the addition of those 2 infinities is not an issue, but what we essentially have is infinity minus infinity over infinity. And that's indeterminate, so we can still apply L'Hopital's rule. So on top, if I apply L'Hopital's rule, I have 2e to the 2x minus 2x. On bottom, I end up with e to the x plus 1. And in here, this is still in indeterminate form, right? Because when I plug in infinity, I have infinity on the top. Well, so I have infinity minus infinity over infinity still. But if I apply L'Hopital's rule again, let's see. So limit as x approaches infinity of 4e to the 2x minus 2 over e to the x. Well, that's still just infinity over infinity. It's better now, right? There's less infinities, but it's still not good enough. So let's take another L'Hopital's rule. So limit as x approaches infinity. This now becomes 8e to the 2x over e to the x. But notice now that I can simplify this. I can simplify this, and this becomes the limit as x goes to infinity of 8e to the x, right? These two right here, subtract the exponents. And now, at that point, well, plugging in infinity, I end up with infinity, right? There's nothing crazy about that. But what I mean is, this is not in indeterminate form, right? We know infinity is infinity. So weird manipulation here of multiplying by 1, but also applying L'Hopital's rule consecutively. Let's look at another one. So it's F. G. The limit as x approaches 0 of cosine of x minus cosine of 2x over 1 minus cosine of x. Let's see what happens. Plug in 0. Cosine of 0, 1. 0 times 2, 0. Cosine of 0, 1. So I have 1 minus 1 over 1 minus cosine of 0, 1. So that's 0 over 0. Indeterminate. So we can apply L'Hopital's rule. And when we apply L'Hopital's rule, what do we get? The derivative of cosine is negative sine minus the derivative of cosine is negative, so plus, and because of that 2 in the chain rule, I end up with 2 cosine of 2x. On the bottom, I just end up with negative sine of x. And I just realized this is supposed to be sine because I'm supposed to take the derivative. Alright, 2 sine of 2x. Alright. Now, at that point, let's see what happens. Oh, I forgot my limit. Look at that. Mistakes everywhere today. Limit as x approaches 0. Alright. Now, when I do that, well, sine of 0 is 0, so I end up with 0 plus sine of 0 is 0 and 0. Well, 0 plus 0, there's technically no issue with that, right? That's just 0. But then 0 over 0, that's an indeterminate form. So, let's apply L'Hopital's rule again. And I end up with the limit as x approaches 0 of the derivative of sine is cosine. For similar reasoning, we get 4 cosine of 2x over negative cosine of x. And now let's plug in that 0. When I plug in that 0, negative, well, cosine of 0 is 1. So I end up with negative 1 plus cosine of 2 times 0, 1 again. So 4 times 1 is just 4. And on the bottom, cosine of 0, that's just 1 again. But we have this negative out here. So I have negative 1. So in here, I end up with negative 3. Hold on a second. Oh man, another mistake. The derivative of cosine is negative sine. With this minus, it becomes a plus. The derivative of sine is a positive cosine, makes this a positive 1, makes this a positive 3. There we go. Either way, the point stands. The answer here is positive 3. All right. Let's do another one. That was G. So H. Let's say that I have the limit as x goes to 0 of ln of 1 plus x minus x over cosine of x minus 1. Well, plug in the 0. 1 plus 0 is 1. Ln of 1 is 0. Minus 0 over cosine of 0 is 1 minus 1. So in here we end up with 0 over 0. That's indeterminate. And, well, so we can apply L'Hopital's rule. And what do we end up with? Well, the limit as x goes to 0 of 1 over 1 plus x minus 1 over negative sign of x, right? All I'm doing there is applying L'Hopital's rule, which means take the derivative of the top and the derivative of the bottom. And now let's see what we get. Plug in 0. 1 plus 0 is 1. 1 over 1 is 1. 1 minus 1 is 0. Sine of 0 is 0. But it's in a determinate form, which means apply L'Hopital's rule again. And what is that going to give us? The limit as x goes to 0 of the derivative of 1 over 1 plus x is negative 1 over 1 plus x squared. The derivative of negative 1 is 0, so that goes away. But now, the derivative of sine is cosine, so I have negative cosine x. And now, as x goes to 0, let's see. 1 plus 0 is 1, squared is 1, with a negative, negative 1, over cosine of 0. Cosine of 0 is 1, but with that negative, I end up with negative 1 over negative 1, which is just positive 1. All right. Next one. I. Let's say we have the limit as x goes to 0 of sine of x squared over ln of cosine of x. Well, let's see. We're going to 0, right? 0 squared, 0. Sine of 0, 0. Cosine of 0, 1. Ln of 1, 0. So look at that. 0 over 0. So apply L'Hopital's rule, right? That's indeterminate. So L'Hopital's rule, we get, and here the derivative of sine is cosine, but then by chain rule times 2x over, look at that, I cut it early. I forgot to write my limit. Limit as x goes to 0, there we go. The derivative of the top, then on the bottom, the derivative of ln of cosine of x. So in here I'm going to have 1 over cosine of x times the derivative of cosine, negative sine x. All right. So let's see what we get now. In here, sine over cosine is tangent. So what we really have here is the limit as x goes to 0 of 2x times cosine of x squared over tangent of 0. Not tangent of 0, tangent of x. All right. And well, as written, that if I plug in the 0, 2 times 0 is 0. Cosine of 0 is 1. Tangent of 0 is 0. So overall, I end up with 0 over 0, right? Which is indeterminate, right? Now, oh, wait, negative. There we go. Negative tangent. All right, which is indeterminate. So because of that, we can apply L'Hopital's rule again, right? So applying L'Hopital's rule again, we end up with, well, the limit as x goes to 0 of the derivative of the top over the derivative of the bottom. On the bottom, easy, negative secant squared of x. On the top, however, we're taking a derivative, so I gotta do the product rule. So the derivative of the first times the second plus the derivative of the second, which is going to be negative 2x sine of x squared times the first, 2x. All right, let's see what happens now as x goes to 0. So we have 2 times cosine of 0. Cosine of 0 is 1 plus 2 times 0. Ooh, doesn't matter what the rest of this is. I'm multiplying by 0, so 0. And actually, they're all zeros, right? Sine of 0 is 0. 2 times 0 is 0. 0. And on the bottom, secant squared of x. Well, secant of 0 is 1. 1 squared is 1, and with that negative, I end up with a negative 1 here, giving me my solution of negative 2. And, oh, excuse me. And that will be the final answer there. J. Let's say that, well, let's look at a different kind of scenario here, right? Let's say that I have the limit as x approaches 0 from the right of sine of x to the x. And in here, well, if I plug in 0, sine of 0, even if it's from the left to the right, sine of 0 is 0. And then to the 0. That's an indeterminate form. So we need to figure out what to do with this. So let's see. The first thing I'm going to do here is I'm going to say, well, let y be equal to that limit. The limit as x goes to 0 from the right of sine of x to the x. At this point, what I'm going to do is I'm going to take the natural logarithm of both sides. So I end up with ln of y is equal to the limit as x goes to 0 from the right of x ln of sine of x. All right, and now if I plug in the 0, sine of 0 is 0. ln of 0, what does that mean? Well, we're approaching it from the right. So ln of 0 from the right, well, that's going to be negative infinity. But then 0 from the right here is 0. So 0 times negative infinity, well, we need to somehow apply L'Hopital's rule because this is an indeterminate form. All right, well, we already know that L'Hopital's rule only applies L'Hopital's rule only applies to functions, to fractions. And in here, we don't have a fraction, so we have to manipulate this so that we actually have a fraction. So what I'm going to do here is, well, let's take a look at this. A times b, right? I can rewrite this as b over 1 over a. Right? How come? Because in here, I've got something divided by a fraction. Well, that's the same thing as that multiplied by its reciprocal, right? So these two statements are equivalent. So what we can do here is apply that idea here, where this x is that a and the ln of sine x is that b. So, or the other way around, doesn't really matter. So if I apply that, I'll apply it the way I mentioned it first. Right? I just turned it into dividing by a fraction, right? Because it's the same as multiplying by the reciprocal. So in here, if I apply L'Hopital's rule now, and notice we're definitely able to do so because, as we said already, this part right here would be negative infinity, and this part over here would actually also be infinity. So we have a ratio of infinities. So definitely indeterminate still. So we apply L'Hopital's rule, I end up with 1 over cosine of x. Nope, that's not true. 1 over sine of x times cosine of x, right? That's by the chain rule, of negative 1 over x squared. And at that point, well, if I plug in the 0, negative 1 over 0, we don't like that. Cosine of 0, that's fine. That's 1. Sine of 0, don't like that. It's in the denominator. So, well, what I'm going to do here is, well, let's rewrite it because we know we definitely can't plug it in yet. So if I rewrite it, I end up with the limit as x approaches 0 from the right of, I'm going to write this as negative x squared times cotangent of x. All right. So next thing I'm going to do here is, well, plug in the 0. If I plug in the 0, well, 0 squared, 0. Cotangent of 0. Cotangent of 0 is undefined. But since we're approaching it from the right, it actually ends up being positive infinity. But this is still no good, right? Because we still have essentially a 0 times an infinity. So what we're going to do is manipulate it again. And I'm going to rewrite it now. I'm going to be using the same exact trick as before, but I'm going to leave the negative x squared on top. And it really wouldn't matter. And so I have negative x squared over tangent. Noticing here that I wrote tangent, not 1 over cotangent. This is the same exact thing. Now, at this point, now I'm going to apply L'Hopital's rule. If I take the derivative of the top, so we didn't write my limit, the derivative of the top, negative 2x. The derivative of the bottom, secant square x. Plug in 0. 2 times 0, 0. Secant of 0, 1. Good. 0 over 1 is fine, right? That's not in an indeterminate form. So we don't need to take any more derivatives. But now, it may look like we're done, but we are not. Because that wasn't the limit we were looking for, right? The original limit we were looking for did not involve any of this ln stuff, right? It was this thing up here. So what I need to do is, well, since I took the natural log of that limit, I need to undo it. So I have, in here, what we found was ln of y is equal to 0. So that tells me then that y would be e to the 0, which is 1. So in this case, we found this limit up here to go to 1. All right, next one. That was J, okay. So K. Let's say that I have the limit as x goes to 0 from the right of 1 plus x to the 1 over x. Notice that in here, if I plug in that 0, 1 plus 0 is 1. 0 from the right of 1 over x, infinity. That is in the indeterminate form, all right? That's an indeterminate form. So let's see how to deal with this. So I'm going to say, well, I'm going to let y be equal to that limit, all right? Because we have the variable in the exponent. Essentially, anytime you have the variable in the exponent for logs, for limits, you want to take the log of both sides. So I'm going to start with y is equal to that limit, so that I can take the natural log of both sides and end up with this limit instead. Right? And all I did there was apply the rule of logs, right? Bring the exponent down to the front. This can be rewritten. I'm going to write it simply as the limit as x goes to 0 from the right of ln of 1 plus x over x. All right. Now, at this point, now I'm going to go ahead and apply L'Hopital's rule, all right? And I know it applies. How come? Because if I plug in the 0, ln of 1, 0. Plug in the 0 in bottom, I end up with 0 over 0, which is an indeterminate form. We don't like that. So, L'Hopital's rule. And in here, well, what do I get? The limit as x approaches 0 from the right of 1 over x plus 1, or 1 plus x, right? Same thing, over 1. And as we approach 0, well, 0 plus 1 is 1, 1 over 1, 1, and then over 1, 1. Okay. But that was not the limit we were looking for. We were looking for this other limit. What we found was ln of that limit. So if I have ln of y is equal to 1, this tells me that y is equal to e. So that's what our limit goes to there. Right? All right, so that concludes L'Hopital's rule and indeterminate forms, which was 5.6.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.